Hi, my name is John Bolte. I'll be speaking today on the topic of agent-based modeling, particularly with respect to the analysis of coupled human and natural systems. I'll be speaking from our experience developing Envision, a modeling framework and software platform developed at Oregon State over the last 2 decades that supports a multi-paradigm approach to modeling, including multi-agent-based representations. This presentation will focus on several areas. The overall theme of this presentation is to identify some key areas for the evolution of agent-based models. To do so, I will start with a little bit of background on how my group and various partners have been using agent-based models within the context of our work, which is focused on developing models and modeling tools supporting the analysis of coupled human and natural systems, or CHANs. In our case, we use agents, what we refer to as actors, to represent human decision makers managing landscapes in dynamic simulations, what we refer to as alternative futures analyses. We use a tool called Envision for conducting these simulations. We have been developing Envision and applying it to the analysis of a wide variety of CHANS systems over the last 2 decades, and in the process have developed a multi-agent-based subsystem that runs in parallel with other biophysical and/or socioeconomic models to simulate the dynamics of these coupled systems in a spatially explicit, policy-oriented framework. We've taken a fairly practical approach to building agents, and I'll relate a bit on how we think about and utilize agents in Envision as a way of providing context for some thoughts on future directions. Here's a schematic of one example of a CHANS, a coupled human and natural system, in this case examining water supply and demand in Oregon's Willamette Valley, that demonstrates the representational needs for a typical CHANS project involving agent-based models. Note the need to represent both biophysical processes such as hydrology, vegetative dynamics, and climate change, and human system processes such as land allocation and water consumption. Decision makers in this dynamic landscape are represented by actors with knowledge of the landscapes they manage and decision-making authority on land and resource management. These processes collectively drive landscape change. An important aspect of these systems is the variable coupling between the biophysical and social cultural dimensions of the landscape, as well as the recognition that location matters. Envision was designed to enable spatially explicit, coupled modeling of these often complex systems, providing support for plug-in models of landscape change and landscape productions, with a multi-agent-based capability focused on policy selection and policy decision-making. This slide provides a summary of Envision's architectural components. Envision is a framework providing support for spatially explicit mixed paradigm modeling, particularly useful for analysis of coupled human and natural systems. It contains a spatial temporal data engine for representing GIS-type data in an application, a plug-in architecture for including modeled representations of biophysical and social economic processes, a multi-agent-based modeling subsystem, and, for at least the desktop version of Envision, a set of visualization tools for dynamic maps and charts. Envision consists of roughly 1 million lines of source code written in C++. It is 100% open source, and the source code for Envision is freely available. Most relevant for the discussion today is Envision's approach to representing actors. Actors in Envision represent entities in a landscape that make decisions about how specific areas within that landscape are managed. They do this within a multi-objective decision-making framework where individual agents can be configured to balance landscape signals, internal goals, expressions of utility, and/or signals from other actors with whom they share an association. They process this information and then take action or not based on their decision process. A key aspect of an Envision-based simulation is the dynamic feedback loop between actors listening to signals from the landscape, among other things, and the change in those signals resulting from the actors' resulting decision-making processes. Envision's support for and integration of multiple modeling paradigms is key here, as typically these signals result from running biophysical and/or social economic models in parallel with the actors' decision-making processes. Envision actors' primary behavior is making decisions about landscape management. They make their decision within the constraints of policies that are available to them that define decision alternatives and the rules the actors conforms to. The decision process an actor uses to select a policy can be relatively simple or complex, and can take into account dynamic landscape signals representing a set of application-defined landscape performance metrics, or the actor's internal value system, or resource constraints, cost-benefit analyses, and/or other relationships to other actors. For decision-making, Envision supports multiple paradigms for actor policy selection and decision-making that can be mixed or matched depending on the needs of a particular analysis. These paradigms include altruistic and self-interested decision-making, a utility-based cost-benefit approach, influences arising from other associations with other actors, and/or placement within a influence network or social network. One of the needs we see in this area is continued formalization of decision-making paradigms, particularly with respect to defining behaviors in AVMs. Parallel to this is the need for standard-based tools for representing agents and their behaviors in simulations. We are currently exploring representations for adaptive influence networks in Envision, extending the current actor model to include both resource management decision-makers, individual actors, as well as additional network actors that do not make decisions but influence the decision-maker's decision process. The current implementation provides for the propagation and application of, or attenuation of, landscape signals through the influence network based on the topology of the network, using either a static network, which remains fixed through time, or dynamic adaptive networks for which the topology for the network evolves through time based on a learning rule. We are trying to understand and model how influence is propagated through these networks and how it influences the decision-making of local actors based on looking at real-world networks as well as modeling different signal propagation strategies. We see this as an area with needs on both the empirical and modeling sides. The dynamics of adaptive networks is another emerging area where we see interesting possibilities. Some of our work focuses on developing strategies for managing landscapes in wildfire-prone areas, common throughout the West, particularly in areas near the rural-urban interface or other areas with significant human influence. We've seen examples of highly adaptive fire management networks emerge in response to increased fire risk in these areas, as well as to examples of poorly or maladaptive networks emerge in these areas, begging the question, are there fundamental principles that drive the organization of these networks towards more or less adaptive structures? We see a need for better models for exploring dynamic network organization in these actor networks, as well as the need for more longitudinal studies tracking the dynamics of real-world actor networks. Thinking a little further, here's some important trends that may have implications for agent-based models. First, data is becoming ubiquitous, all kinds of data, and more of this data is becoming available in real or near real time. Our agents will start utilizing this data to have more information at their fingertips. And as data becomes more real-time, the agents will increasingly be called on to get involved in real-time decision-making, perhaps in consultation with other agents. Second, machine learning is becoming commoditized. Very powerful learning algorithms are available and easy to use, from Python libraries to cloud-based packages that provide access to prodigious computational capabilities via pretty simple scripts. Our agents will get smarter and able to make better decisions, probably better decisions than we can. Third, we are getting more connected, and our agents will get more connected as well, both to data sources and other agents via negotiation and consultation. And finally, models are increasingly being used not just for simulation, but as components of control systems that can modify the real world based on feedbacks. We already see this in automated systems for trading equities, and we see this as an emerging trend that ABMs are well suited to take advantage of. Overall, agents in a computer science sense will increasingly resemble agents in an ABM sense, and both will become more engaged with the world and other agents. We see the emergence of increasingly intelligent agents as a key feature development in ABMs. These may learn offline and bring that knowledge into an ABM, or may use model representations of reality to learn within the context of a particular simulation. We believe that agents and actors will increasingly incorporate internal models of their worlds via machine learning, allowing for more flexibility and adaptability in responding to real-world signals. This is a really interesting area with many opportunities to engage sociologists, computer scientists, data scientists, and others. The rise of big data will facilitate this, providing increasingly fertile ground for agent learning. Additionally, inter-agent learning, where agents learn from the actions of other agents, opens up possibilities for emergent collaborative decision-making between agents as well. That is an interesting area to explore. Finally, we believe the move towards increasingly more intelligent agents and the rise of ubiquitous sensing systems will facilitate the direct use of ABMs in real-time information control systems, sharing information and perspectives and making decisions collaboratively. I think this is where things will really start to get interesting, and there's a strong need for models grounded in data that will allow for understanding how these increasingly intelligent, increasingly connected, and increasingly data-aware systems operate and react. ABMs provide an important testing ground for mechanistic theories of self-organization, reorganization, signal processing and complex systems interactions, and control, and the development of these theories is critical to developing robust real-world systems. And with that, I'll close. Thank you very much.